My name is Sofiane Abbar, and I'm presenting our system paper titled QARTA, a machine learning-based system for accurate map services. This work is about maps, about routing, and travel time estimation. This has been done in collaboration with my colleagues Mash'al Musleh from the University of Minnesota, Radis Stanojevic and Mohammed Muqbil from Qatar Computing Research Institute. Some motivation and background about this work. Back in 2011, Qatar won the bid to organize the 2022 FIFA World Cup. This was a huge moment for celebration. Right after it, the country undertook a massive and ambitious project to expand its infrastructure by building cities from the ground and expanding the capital Doha, which is home to 90% of the population in the country. The country actually increased the size of their road network 3 times in 5 years. This was massive, and this resulted in frequent changes and updates to the road layout with a lot of deviations, new roads, and new closures, which also caused huge congestions and frustrations among the drivers that we all experienced while living there. So this was so bad that this comic actually made it to one of the most popular newspapers published in the country, where it depicted Google Maps as a turtle, and then the company that's in charge of building the roads called Ashghal as a rabbit, and it shows how Google Maps is struggling to catch up with the frequent and the fast changes that are happening to the road network. Thus, we decided to create QARTA, which means map in Arabic, or kharita, which leverages big spatiotemporal data and machine learning to build a map engine that understands routes, traffic, and drivers. QARTA is deployed in 2 major companies in the country: the national taxi company that operates 4,000 vehicles, and the delivery company that has 3,000 motorbikes. So QARTA receives around 2 million queries per week and collects around 1 million GPS points per day from the different vehicles that uses it. These are real screenshots from some of the applications that are downloaded by hundreds of thousands of users in the country. So routes, fare estimation, and ETAs are all powered by our engine. In terms of architecture, QARTA is built around the map, which is the central entity of our system, and is built in 3 layers. The first layer is the data layer, which does data collection from different sources and does some data processing and preparation. The second layer is the map making layer, which is in charge of several machine learning components. The last layer is called query calibration layer. This one is in charge of calibrating and tailoring the results of different queries to the context of the user. So let me start with the data layer. Actually, what we observed when we started working with spatiotemporal data that come from real fleets is that existing efforts toward data cleaning and wrangling do not support well spatial and spatiotemporal data. Thus, we developed our own rule-based system to clean the trajectories and the GPS data we were collecting. Examples of these rules include the following. Trajectories with a stop, for instance, are always split into 2 sub-trajectories. We try to filter out some unrealistic points by removing them from the trajectories, and we also try to figure out when we have missing data in our trajectories. Next is the map making layer. The first module I'd like to describe is the edge weight module. This one is in charge of combining the road network and the data that we collect from our fleet in order to generate a rich map with richer metadata about the different speeds at different road segments observed on different times of the day and different days of the week. In practice, the road network is represented as a directed graph, and then the data that we collect from our fleet comes in this format where we have the time at which the trip started, and then the pickup location, the drop-off location, the distance, and probably the actual duration of the trip. Now, given this, what we aim for is to generate multiple versions of the graph, weighted this time, for different hours of the day or different hours of the week. In practice, what we do, or the way we solve this, is to write an equation for each trip that we have. So say that we have trip I that actually took a certain duration, di, let's say it's 23 minutes. This di, or these 23 minutes, should be equal to the sum of the durations of the different edges E1, E2, EK on the path of that trip. Then we should be able to solve a system of equations where we have the similar equation for each trip, and the objective here is to try to minimize the difference or the square difference between the actual durations and the approximate ones that we are trying to predict. The second module we have in the map making layer is the metadata imputation module. Indeed, what we observed is that public maps like OpenStreetMap have very poor metadata coverage. All the road segments here marked in red are roads for which we don't have the max speed, for instance, or the posted speed. So the objective is to try to infer these metadata using machine learning algorithms and exploiting the GPS data that we have from our fleet, which drive around the different neighborhoods here. The third and last layer in the system is called query calibration layer. Now, estimated time of arrival is extremely important. Let's take an example of a map service like OSRM, and let's say that we have tens of thousands of trips that we recorded for which we know the actual travel time. So this is the ground truth duration of the different trips, and here in the y-axis what we post is the travel time returned by the map engine. What we observe here is that for trips that took actually around 30 minutes for most of them, OSRM would actually predict something around 10 minutes to 20 minutes, and this is expected because OSRM doesn't have access to proprietary information or data about traffic. We ran the same experiment with Google Maps. Sometimes Google Maps overestimate or underestimate in other cases. Because ETAs are very important for route planning, logistic and deliveries, fair estimation that need to be done beforehand, and we figured out that actually this ETA or the actual ETA of a trip depends on a couple of parameters like the time of the query, the locations, where the user is, where is he going, the route that will be picked by the routing engine, the type of the vehicle, maybe the weather conditions, and so on and so forth. Thus, we asked the following question: can we learn the per trip ETA offset, like the difference between the actual duration of a trip and then the predicted duration of trip given by different map services? And if we can do that, can we then use that kind of model that we would learn in order to calibrate the queries at query time? So we came up with a system based on supervised learning, where actually we create training data by doing the following. So for each trip that we have in our data, we compute the difference between the actual duration and the estimated duration that we got from the routing engine like Google Maps or OSRM. And then we crafted a bunch of features like temporal features, like here the hour of the day, and then we also cluster the locations, or we partition the area into different zones, and then we say, this trip actually the first one went from zone 14 to zone 53. Why? Because different zones may be impacted differently by traffic at different times of the day. Now, the way we use this in production for shortest path queries, for instance, is when we have the request or the query of the user that has the origin, the destination, and then the start time. We take this query, we push it to OSRM to get a route and an ETA that doesn't have traffic information. At the same time, the query goes to our feature extractor module to build a feature vector V that we will be using actually to compute the offset delta, and then we combine this offset delta with the ETA. Now, in terms of experimental evaluation, we use data from the actual fleet that uses our system, in this case from the taxi company. We took around 250,000 trips for all our machine learning models. We trained on 80% and then we tested on the remaining 20%. And for the underlying algorithms, we used like OSRM for shortest path, we used OpenStreetMap as the base map, and then we just implemented off-the-shelf KNN and range queries. Our first evaluation was on shortest path. So what we wanted to do here is to figure out which of the engines produces more accurate ETAs. We report both the median and the mean relative errors in percentage. So the first system that we tested is OSRM, and it achieves a median of 46% relative errors. Google Maps does much better, and its median relative error is around 16.64%. QMap is nothing but OSRM that consumes our map with our edge weights, and we see just by doing that we can actually reduce the error from 46% to 19.6%, which is a huge drop. QCalib is also another version of OSRM that uses no traffic information, but where we use the calibration at the end of the process, and this actually turns to be extremely effective as it pushes the error further down to 16.35%, making it slightly better than Google Maps. Finally, QARTA, which combines both the calibration layer and the edge weight, achieves the lowest errors in our evaluations with 15.61%. We ran also other evaluations for KNN queries where we actually try to assess the precision, which is the number of items that are returned that should have been returned in the ground truth, and we see that the precision of QARTA is much better than OSRM and Google. And we also had an evaluation where we compared the rankings that are produced by the different systems like QARTA, OSRM, and Google, and we see that QARTA is also doing better. There are also a couple of other experiments that you could find in the paper. Thank you very much for your attention, and please do not forget to attend our demo.